Okay, let's begin. So refresh our memories about what we spoke about last time. Key ideas. We spoke about what critical points were. What is a critical point? Great. Point where
Y prime is equal to 0.
what?
Is it where y prime is equal to 0?
That's half the answer. Or undefined. These guys are critical points. Now, Fermat's theorem tells us that whenever the derivative exists, so Fermat's theorem was also something that we looked at. It says if f prime exists and x equals c is an extreme point, then f prime of c is going to be 0. But we also know that we can have extreme points where f prime is undefined. For example, at the absolute value of x. We also have cases where the derivative is 0, but it's not a max or a min. For example, at the origin with y equals x cubed. So, because the derivative is 0 is going to be of special interest, but also when the derivative is undefined is of special interest because the absolute value fall in this category. We designate such points to be critical points. These are going to be the points that we want to test where maximums and minimums occur. We also spoke about absolute extrema versus local extrema. Right? And we saw something called the extreme value theorem that says we're guaranteed absolute extrema. On A, B, if f is continuous on A. And with the understanding it may occur at the endpoints, it may occur at endpoints. Then we spoke about the closed interval method. As a way to actually find the absolute extrema of a continuous function on a closed interval, which the extreme value theorem guarantees that we will be able to find. And I gave you some examples of actually attempting to do that with two functions. But first, I think, because it includes finding critical points, maybe let's just do an example first where we're finding critical points. So let's actually do that, and then we'll go back to the example that I had you guys do at the end of the class. So at the end of the class, the main thing was talking about extreme points, local and absolute. Local just means you're a max or min in your local region. Absolute means you're the max or min on the entire region. And absolutes are guaranteed in the extreme value theorem, and the closed interval method is how we can find them. We'll talk about how to find local extrema. If not this class, for sure the next class. But right now, let's just focus on one part here, which is very important. It's critical. We need to know how to find critical points. Let's do some examples. And we're going to do a few because I want to make sure that you understand this. A. Y equals C, where C is a constant. B. Y equals X, C. Y equals the absolute value of X. D. Y equals X cubed. E. Y equals the sine of x. Let's do that on 0 to 2 pi. F y equals tangent x. Let's do that on the interval minus pi to pi. G y equals the square root of x. H y equals x to the 4th minus 4x squared. We're going to go through, we're going to find all the critical points of all those functions that I just mentioned, and hopefully by the time we get to example 8, you fully understand what it means to find a critical point. If not, you need to go to 2 today. So, let's actually start. So basically everything I mentioned here, you need to know the definitions and the statements of them. You need to know what is a critical point. What does Fermat's theorem say? What is an absolute versus local extrema? What is the extreme value theorem? You don't need to know how to prove any of these things, but you need to know what they say, what their definitions are. And you of course need to know the closed interval method, which we will get to. Let's find some critical points. Y equals a constant. Okay, how do you find the critical points? Yep.
You take the derivative of the constant, which you get 0. But yeah, you take the derivative,
Okay.
and then set the derivative equals 0, and then whenever it's 0,
Yes, you're still thinking of half the rule. Think of the whole rule. For critical points, we're going to set y prime equals 0 or y prime is undefined. Okay, think of both of them all the time, right? Now, in this particular case, y prime is never going to be undefined because it's actually going to be 0 all the time, but you have to consider it. You don't know ahead of time. So here I get y prime is actually 0, which means, so it's never undefined, so that's the first thing you should realize, always defined. And that's what tells me that I don't have to worry about that case. Secondly, if y prime is 0, at what points is y prime is 0? This means y prime is 0 at all points. What does that tell you about the critical points of this function? All x, all real x are critical points. Right? Every single point in this function is a critical point. Now, so your function would look like that. Let's say you're on the xy plane, passing through C. No matter what point I have, it's a critical point. Now, constant function is kind of a weird situation. Basically what a constant function, how you can think about it is, every single point on the function is both a max and min. Every point is larger than or equal to every other point, and every point is smaller than or equal to every other point. So literally every point satisfies the definition of a max or min. So that's kind of a weird situation, but it's one you should be aware of. E. Slightly more interesting, but not quite. How do you find the critical points? For critical points, we're going to set y prime equals 0 or undefined. You always start that way. That's what it means to be a critical point. Now here, if I find y prime, what is it? 1. Now, this is always defined. writing this in green because you don't have to actually write it out. I mean, you can see it. But I just want to make you aware that now that means I do not have to consider that situation. Now, what are the critical points? Y prime is never 0 for all x. So what does that mean? No critical points. A function does not have to have a critical point. This one has none. There is no point that fits the definition. There is no point where the derivative is 0, and there's no point where the derivative is undefined. There are no critical points for this function. Y equals epsilon x. Critical points. Y prime equals 0 or Y prime undefined. What is Y prime here? Michael?
It's negative 1, negative, positive 1,
Right, so piecewise. If your x is less than 0, it is going to be negative 1. If your x is 1, it's going to be that. And you'll notice that at x equals 0, it's undefined. This graph looks like this. So, what are the critical points? X equals 0 is the only critical point. At 0 is the bad part. 0 is where we break continuity. The derivative is not continuous at that point. It is undefined at that point.
Doesn't the graph look like a V?
I'm graphing the derivative here. This is Y prime.
Oh,
Yes, the original graph, if I graph Y, that is a V. But if I'm graphing the slope over here is positive 1, the slope over here is negative 1. So that's the graph of the function, this is the graph of its derivative. The derivative is undefined at 0. So, an example we've talked about many times, we know why it's defined at 0, you've literally computed the limit. So this one has one critical point. It occurs at x equals 0. Notice that Y prime is never actually 0 here. So I know that this part doesn't check out, but that part actually gave me an answer. That's why you always think about both, right? So don't just think half of the rule. Oh, I just want the derivative to be 0, because then you might conclude here this has no critical point. Think of both of them, consider both all the time, because you never know which one is going to check out. For critical points, what do you do? Set Y prime equals 0 or undefined. Now, what is Y prime here? 3x squared. Notice it's never undefined, so I don't have to worry about that. 3x squared is a polynomial, that's always defined, it's always continuous. So now what I'm going to do is set Y prime equals 0. This means 3x squared equals 0, and this means x equals 0. What is y prime? Cosine. Cosine of x, always defined. Set cosine x equals 0. This means that your x equals pi over 2 and 3 pi over 2. Right? In general, cosine x equals 0 for x equals n pi over 2, where n is odd. That's something you should know. So every odd multiple of pi over 2, our cosine will hit 0. Within that interval, it'll hit 0 at these 2 points. So those are the critical points. Now yes, like I said, technically it's not a point, but sometimes you refer to it that way. There are contexts in which you definitely want to find the corresponding y value. What I would do is just take pi over 2, plug into here, I get 1. So the critical point is pi over 2 comma 1. Then I would take 3 pi over 2, plug into here, I get minus 1. The second critical point is 3 pi over 2 comma minus 1. So specifically, pi over 2 comma 1 and 3 pi over 2 comma minus 1 are the critical points. Which makes a lot of sense if you remember what the sine graph looks like. That's saying here and here the derivative is 0. You'll also notice that that's where a max and min is located. Critical point. Set y prime equals 0 or undefined. 1,000 times. You're going to write that down every time you're doing this problem. By the time you get to a test, you'd have written that statement 1,001 times. It's something that's going to be burned in your brain to the point where even if you're anxious, still you're sweating bullets, you're going to remember. That's how you're supposed to be studying. Write down the rule you're thinking about, the strategy you're thinking about every single time when you're doing a problem. That way it gets burned into your brain. The rule becomes very natural for you. It's just something that you do by feeling. You don't have to think about it after a while. That's where you want to be. Now, like when you were kids, you were learning your ABCs. It's a very painstaking process. You're learning your grammar rules, subject verb agreement, very painstaking process. Suddenly now you can talk and you don't have to worry about it. Right? You don't even think. I'm not like thinking subject verb agreement while I'm talking, right? Because it's very natural. The rules have been drilled into my brain so many times. I can just do it now without even thinking about it. So that's where you want to be with the math. And this is how you get there. State the entire rule every single time. Say it to yourself every single time. Memorize the rule every single time. If you're in a test and you have to think about what you need to do, you didn't study enough, right? So even if you can get through a test by really thinking hard and getting an A, it's not a good A. Because what that means is there's a possibility I could have tricked you. And you don't want that. You want to guarantee that you know what you're doing. What is y prime? Secant squared of x. Okay, so secant squared x equals 0 versus secant squared x undefined. What are the x values that make secant squared x 0? Huh? Okay, so what does that mean? None. Right? Secant is 1 over cosine. So it's a fraction where the numerator is always 1. It will never be 0. A fraction can only be 0 when the numerator is 0. Secant is a fraction where the numerator is always 1. It's never going to be 0. Where is it undefined? Pi over 2 and minus pi over 2, at least in this interval. Because the secant is 1 over cosine, it is undefined whenever the cosine hits 0. Cosine hits 0 at every odd multiple of pi over 2. So plus or minus 1 pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, etc. Within between minus pi and pi, those are the two values. Critical points. Now, of course, you can kind of see what's going on here. Pi over 2 for the tangent, there's an asymptote, minus pi over 2. There's also an asymptote. If I make this minus pi and make that pi, the tangent graph looks like, you should know, looks like this. Then it will come down here, hit there, it will hit 0 at minus pi, 0, and pi, because the tangent will hit 0 whenever the sine hits 0, and the other part will come like that. So, clearly the derivative is undefined here and here. The function itself is not even defined. And we know where the function is discontinuous, so is the derivative. So, your derivative is undefined here, and there are no critical points. Now, you might be tempted to say that 0 is a critical point because, you know, the middle kind of looks like x cubed, and I know x cubed has a critical point there. The problem is that this guy rises a lot faster than x cubed. The x cubed kind of flattens out, but not quite. And so that might be a little bit of a difference here. The only critical points are the minus pi over 2 and pi over 2. What is y prime here? So, where is that 0? Nowhere. It's never 0. Where is it undefined? X equals 0 makes it undefined. Now, I wouldn't have to worry about negative x's because it's not even in the domain. They would never actually be considered in the first place. So x equals 0 is going to be our critical point. Which, as you might recall from the square root function, is actually our absolute minimum. So we would have figured it out by doing that. H. All right, 1 minute, do this. Do it now, 1 minute, quickly. Besides Wendy and Naeem, did anyone come in after I called roll? What's your last name?
Rolle. A-R and getting to B-L-O.
Okay, I got it.
You'll skip that.
Okay.
Oh, which is fine.
Time's up. What's the answer? Huh?
Negative radical 2, positive radical,
Negative radical 2, positive radical 2,
and 0.
0. Okay, let's see. How do you find critical points? Y prime here,
Or 3 minus 8.
okay? So it's never undefined, that's a polynomial, so I don't have to worry about this. So how do I find critical points?
You set it equal to 0.
Solve.
After out 4x.
Minus,
2 equals 0, and then you set each factor.
right, so x equals 0, or x equals plus or minus radical 2. Critical points. If you did not get that within the minute, go to tutoring. Go today. There's going to come a point where finding the critical points is just going to be one small part in a much larger problem. You want to be able to do this very quickly. Hopefully now we understand how to find critical points. Let's move on to the example from last time. Actually applying the closed interval method, which we know involves finding critical points. Let's compress this a little bit. I'll give you two functions where I wanted you to find the absolute extrema. So one was y equals x to the fourth minus 4x squared on the interval minus 1 to 3. The other one was y equals 2 sine x minus cosine 2x on the interval 0 to 2 pi. So let's start with this one. Y equals x to the fourth minus 4x squared on minus 1 to 3. What's the first thing you do to find the absolute maximum? Critical points, going to be the first thing. How do you find critical points? Y prime equals 4x cubed minus 8x. Set y prime equals 0 or undefined. It's never undefined. This means that my 4x cubed minus 8x must be equal to 0. This means that my 4x x squared minus 2 must be equal to 0. This means that my x equals 0, my x equals minus minus radical 2, or my x equals positive radical 2. Now, at first, I'm going to ask a question that might be a little bit strange, but what are the valid critical points here?
Valid?
Huh?
Valid.
I guess the critical point.
Huh?
0 and radical 2.
0 and radical 2. I would actually ignore this one. Why? Huh? Radical 2 is 1.4. So this guy is not in the interval. So he doesn't, I don't care, not in the interval. Right? So that is a critical point of the function, but it's not one that I care about at the moment because I only care about all x values between minus 1 and 3. That's not between minus 1 and 3, so I'm going to ignore that critical point. So the only valid ones are 0 and radical 2. Now once I find the critical point, what am I supposed to do with it?
Evaluate.
I need to evaluate the function at the critical points. So I am going to call this f of x. I'm going to evaluate f of 0, which is going to be 0. I am then going to evaluate f of radical 2, which is going to be, if I plug in radical 2 here, I would get 4. Plug in radical 2 here, I would get 8. And so that's minus 4. So step 1 in the closed interval method is to find the critical points and evaluate the function at the critical points. This was step 1. Step 2 was the next thing we're supposed to do.
Evaluate the function.
You need to care about the endpoints. Because you might have one of those situations where the function actually hits its peak at the part where the interval cuts off. And here, you know the endpoints, so you're just going to evaluate it. So I'm going to find f of minus 1, and I'm going to find f of 3. Now f of minus 1, that's going to be 1 minus 4, that's minus 3. F of 3, 3 to the 4th is? Yes. Maybe there's a nicer way to do this. So this is 3 to the 4th minus 4 times 3 squared. Notice that 3 squared is a common term. If I factor that out, I'll be left with 9 minus 4. And so that's 9 times 5, which is 45. Right? So it's 45. Okay. What is the third step in the closed interval method? Compare. Of all the y values I found, I want to identify the largest and the smallest in this situation. Radical 2 gave me the smallest. Largest? This one. This means the absolute max is going to be f of 3 equals 45. And the absolute min is going to be f of radical 2 is minus 4. And that is your answer. Any questions on this? Okay, so a problem type of this type will be on the next test. It will be on the final. So make sure you get what happened here and why it happened. I'm going to put it on the next quiz. I'm going to put it on the next test. 99% sure it's going to be on the final. I'm not writing the final, but it's one of those things. Shows up on pretty much every final. let's actually just illustrate this. Now we are going to learn to graph things in greater detail than you've ever done before, assuming you've never done Calc 1 before. But let's just graph this in a naive way, like the pre-calc way. This is just me reminding you of how to graph things here. Let's just illustrate the point here. If I wanted to graph that function, how would I do it? It's the first thing you want to look for when you're graphing a function. Y-intercept and the x-intercepts, right? So you have x-intercepts. This is when y equals 0. So this means factor out x squared. This means your x equals 0 plus or minus 2. So the first thing I'm going to do, 0 plus 2 minus 2. Of course, your y-intercept here is automatically going to be 0. Okay, what do you do next? Come again? Well, y at those points is 0. I already know that. Yeah. Number line? Yeah.
Number line.
And do what?
See where is positive and negative.
Right. Specifically, like Michael said, at points in between. I already know at those points it's 0. So what I'm going to do is I'm going to test points in between. So I'm going to try test minus 3, minus 1, 1, and 3. And I'm going to plug that into the original and see what I would get. Now, both minus 3 and positive 3 is going to give us the same thing. We actually computed that before. That's already positive. So that is going to be, and let's say we didn't compute that. There's actually a nicer way to actually see it. What you'd want to do is you want to write the function in factored form. So this would be x minus 2, x plus 2. So what you would do here is you plug in minus 3. Now you don't care about the actual value, you just care about whether it's positive or negative. You square it, it's going to be positive. Minus 3 here is going to give us a negative. Minus 3 here is going to give us a negative. So you have a positive times a negative times a positive. That is going to be positive. So your graph is up here. Notice that because all the powers are even, the same thing is going to happen at plus 4 minus 3, so your graph should be up here over there. Plug in negative 1, positive, negative, positive. That's negative. Which means in this region your graph is down here. And because, again, even powers, the positive and negatives will behave the same way, so if I tested 1, I would also get the answer down here. So you have a graph that passes through those 3 points, and it's in those locations marked by the x's, and we know that polynomials are very curvy, so the graph ends up looking like this. So that's how a pre-calc student sketch this graph, right? We're going to learn to do this in a lot greater detail, but for now, that's a very naive sketch of the situation. Now, what did I ask in this particular problem? I asked you about what's going on at minus 1 and what's going on at 3. So if I were to cut that off, so at 3 it's going to be somewhere up here, and I actually want to ignore that. Over here, where do you think this is going to be? What's the location of that?
Radical 2.
Minus radical 2. How do you know it's minus radical 2?
Because the slope is 0.
The slope is 0, and we know by Fermat's last theorem, that's a minimum point there, and the derivative is definitely defined as a polynomial, so that means the slope has to be 0. So then I ask myself, where is the slope 0 in that kind of location? It occurred at minus radical 2, which means minus 1 happens before, which means the cutoff is going to be somewhere here. Now, I want you to appreciate that that's going to be below that point here. So what we are actually looking at is this graph. That's what we're actually seeing. Okay? I don't care what happens outside this window. This is why I ignored the negative radical 2. Doesn't apply. This is the beginning of the universe. That's the end of the universe. Now, can you tell me what the absolute max and min are? Well, you can see from the picture, that has to be an absolute min. You can also see from the picture, this has to be the absolute max. And I figured that out without sketching the graph. Which is important, because sometimes graphs are really hard to sketch. Right? So without even knowing what the picture looked like, I could actually identify where these points occur. Right? That's the power of the closed interval method. I don't have to go through all this to figure it out. So that's how I figure out the absolute max and min for this function. By going through these calculations, I can actually identify the specific points where this kind of property occurs. Let's do it again. Let's do it for this guy. Any questions on this one? Well, okay. I want the absolute max and min of this function. What is the first thing I'm going to find? Critical points. How do we find critical points? Set the derivative equals 0 or undefined. So I'm going to find y prime. What is y prime here?
2 cosine x. Plus 2 sine. Oh, yeah, 2 sine.
So now I am going to set 2 cosine x plus 2 sine 2x equal to 0 or undefined. This is a sine and a cosine. It's never undefined. So now my concern is what values of x makes this 0? How do I solve? Find the x that makes that 0. Yeah.
I subtracted 2 sine 2x, eliminate the 2's, and then
Okay, you can eliminate the 2's.
I turned sine 2x into 2 sine x cosine x, and then
So you did this.
yeah, and then I turned sine 2x into 2 sine x cosine x, so it's negative 2 sine x cosine x,
Okay.
and then you divide by cosine x, and you can divide by negative 2 as well, and that gives you negative 1/2 equals sine x.
No, critical error. What's the critical error?
Oh wait, it's because I divide by cosine.
You divide by cosine. Does cosine ever hit 0 on this interval? Yes, it hits 0 twice on that interval. So you just doubly divided by 0. Not how you would go about it. You're almost along the right lines. You just need to tweak a little bit. How do you solve an equation set equal to 0? What is the first thing that comes to mind? I give you a random equation. Something equal to 0. What do? You factor, and you set each factor equal to 0. So you're not going to be moving anything to the other side. This should not be something you're thinking about. What you should be thinking about is, yes, write this as that by a trig identity, and now factor. You would factor out the common cosine. Because in pre-calc you learned If I want to solve a linear equation, isolate the x. Want to solve any other kind of equation, bring everyone to one side, factor that side, set each factor equal to 0. This is how we solve equations. So, what does this mean?
Cosine of x is equal to 0.
Cosine x equal to 0, which is why it was bad for you to divide by it, or
Or 1 plus
1 plus 2 sine x equals 0. Okay, let's start with this one.
pi over 2, 3 pi over 4.
Pi over 2 and 3 pi over 2. It hits 0 more than that, but I only care about this interval. What about this one? Sine x equals minus 1/2. What is x?
7 pi over 6, 11 pi over 6.
Okay, that is correct. How did we know that so quick? You're supposed to know that that quick, but how do you know that so quick? Quickly, happens in your mind. A couple things you should know. This table should be memorized. Sine theta, cosine theta, theta. Pi over 6, pi over 4, pi over 3. This is your 30 degrees, this is your 45 degrees, this is your 60 degrees. You want to know that sine of cosine of at these special angles. These are called the special angles that happen to not be the nice points on the graph, right? So you automatically should know what sine behaves like at 0 plus pi over 2, pi, 3 pi over 2, and 2 pi. That you should automatically know already from the graph. Other special angles are the 30, 45, and 60 degree angles. Here's how you figure out what sine is at those angles. Count up from 1 to 3 with sine, backwards with cosine, take the square root of everybody, divide everyone by 2. So this tells you sine of pi over 4 is equal to 2 over 2, cosine of pi over 6 is equal to 3 over 2, etc. Right? This tells you all the values of the special angles. So that's the first thing you should know. The second thing you should know is that if I want the sine of theta to be a half, this means my main reference angle, so my reference theta, is going to be pi over 6. Now what that means is that on the unit circle, here's 0, here's pi. Pi over 6 means divide pi into 6 pieces. So I'm going to take the half, divide into 2, and then divide each half into 3. That's pi into 6 pieces. I'm going to do the same thing over here, right? Now I also know that all students take calculus. All students take calculus, which means positive a half is going to be the result if I'm in the first quadrant or the second quadrant. If I want the negative 1/2, which I want here, it's going to happen in the third quadrant and the fourth quadrant at the reference angles, namely, specifically this angle and that angle. Now, what are those angles? Well, you start at 0 and you count off how many pieces of pi over 6 you have. 1, 2, 3, 4, 5, 6 pi over 6s. Boom, one more, 7 pi over 6. Therefore, that's the first answer. Now, to get to this one, starting at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is where that one starts. That's the second answer. Okay? That happens in your head. You don't write that down on a piece of paper, right? But when you memorize things in this way, it's kind of easy for it to happen in your head, right? Because now you know the table. Okay, Where is sine equals a half? Well, the sine is 1, 2, 3, so it's going to be in the leftmost column. That's where the pi over 6 is. So I automatically know my reference angle. Then I remember, okay, all students take calculus. I need negatives in the bottom 2. That means there's a pi over 6 slice on the bottom of here. Well, there's 6 slices to get there, and then that one more is 7 pi over 6, so you're going to think of that. Okay, the next one is going to be the guy all the way on the right. I know a full circle is 12 pi over 6, so one less than that is 11 pi over 6. Right? That's what's supposed to go through your head. That should take you 5-10 seconds. You should have this. Okay? So these are the critical points between 0 and 2 pi. Now what do we have to do?
Evaluate the function.
Evaluate the function. I need to find f at pi over 2. I need to find f at 3 pi over 2. I need to find f at 7 pi over 6. I need to find f at 11 pi over 6. I have enough space. F at 11 pi over 6. What is the f again?
2 sine x minus cosine x.
Okay, so I'm going to go through and I'm going to do that. So this is 2 sine pi over 2 minus cosine of pi. Sine of pi over 2?
Zero.
Sine of pi over 2 is 1. 2 times 1 is 2. Cosine of pi? Minus 1. So here I have 2 minus a minus 1, 3. Over here, 2 sine of 3 pi over 2 minus cosine of 3 pi. Sine of 3 pi over 2. Sine of 3 pi over 2. Cosine of 3 pi. Huh? -1, right? Cosine hits -1 at all odd multiples of pi. It hits +1 at all even multiples of pi. You should know that. So here I have -2 minus a -1 gives me -1. 7 pi over 6. 2 sine of 7 pi over 6 minus cosine of 7 pi over 3, because the 2 cancels the 2 in the denominator. Sine of 7 pi over 6. Well, the reference angle is pi over 6. I memorized that table. Pi over 6 is in the leftmost column. That is going to be 1/2. Cosine of 7 pi over 3. Pi over 3 is going to be the reference. That means I'm going to slice pi into 3 equal pieces. Cosine all students, negative is going to happen in the second quadrant. That means there are 2 slices that work. So it's going to be, the reference angle is going to be, it's the same as cosine of 2 pi over 3, which is just the negative of pi over 3, because it's in the second quadrant. 7 pi over 3. So go all the way around, that's 6 pi over 3, and then 1 more is 7 pi over 3. So the 7 pi over 3 is going to give you exactly the same answer as positive pi over 3. Sorry, I thought that was it. And cosine of positive pi over 3 from the table is going to be also 1/2, right? Because pi over 3 is on all the way on the right side, and the cosine went 3, 2, 1. That's 1 over 2. So this is going to be 1/2. And so that's 2 times 1/2, which is 1 minus 1/2 is 1/2.
Should the sine of 7 pi over 6 be negative?
Did I, 7 pi over 6 is negative, yes. So that's -1 minus 1/2. Someone's paying attention. 11 pi over 6. Okay, quickly do that. One minute, very generous. Okay, time's up. What's the answer? Huh? Huh?
-3 over 2.
This one? Okay, let's see. So Theorem believes it's -3 over 2. Let's check. So we are going to get 2 sine 11 pi over 6 minus cosine of 11 pi over 3. Okay, so sine of 11 pi over 6, what is that? It's -1/2, because I know that sine of pi over 6 is +1/2, 11 pi over 6 is 1 less slice than 12 pi over 6, which is 2 pi. So that brings me in the 4th quadrant. Sine is negative there, so that's -1/2. 11 pi over 3. Well, if I go 1 whole revolution, that's 6 pi over 3. And then I would make 2 revolutions would be 12 pi over 3. So I make 1 less revolution. That's also in the 4th quadrant. So we have all students take calculus. So that's going to be +1/2. And so, yes, these gave us the same numbers, so that's the same thing, -3 over 2. It's not circled yet, but that's that. If you didn't get that in the time limit, what that means is you need to review your trig. So go home this weekend and do trig until you're sick of it. In particular, knowing the graphs, knowing the values of special angles, finding inverse values. Just take your pre-calc book, go to the trig section, and do every problem. And by the end of that, you'll be able to do these in 30 seconds or a minute. Okay, long detour. What's the next step? So we found the critical points, we evaluated it. Next step is to check the endpoints. The endpoints were 0 and 2 pi, so I want f of 0 and f of 2 pi. This is going to be 2 sine of 0 minus cosine of 0, 2 times 0. This one will be 2 sine of 2 pi minus cosine of 4 pi. Sine of 0? 0. Cosine of 0? 1. So this is minus 1. Sine of 2 pi? 0. Cosine of 4 pi? 1. Cosine is 1 at all even multiples of pi. So this is again minus 1. Third thing, compare. Now I have a lot of y values here. I want the biggest and the smallest. What's the biggest? 3. What's the smallest? Huh? Alright, this is the smallest number, minus 1.5. This is also smallest, minus 1.5. So here's how you're going to say that. The absolute max is going to be f of pi over 2 equals 3, comma, the absolute min. You'll say both. So you say f of 7 pi over 6 equals f of 11 pi over 6 equals minus 3 over 2. And that's what the answer will look like here. So this was a pretty long problem. In general, a problem of this type is not going to be that long, but there are going to be other problems that are going to be much longer than this, where finding critical points is just one part of that problem. So you do want to get used to doing the longer type problem, which involves finding critical points at a very early stage. Okay, so that is finding absolute max and min, and we already looked at finding critical points. What is the next thing we want to talk about? The next thing we're going to talk about is very important. Super important. The next thing I want to talk about is, that was what I just did, is a very important theorem. It's called the mean value theorem. I believe, I don't, that's not. I didn't write what section this was. Anyone has the syllabus handy? Never mind, I pulled it up. 4.2. 4.2 is what we're going to do now. The mean value. Affectionately known as MVT. Anytime the math person writes down the abbreviation MVT, he's talking about the mean value. It's a very important theorem. A lot of my professors think that this is the most important theorem in all of calculus, rather than the fundamental theorem of calculus. Not exactly sure I agree with that, but a lot of people have that thought. In fact, as you will see later on, this is actually an important part of proving the fundamental theorem of calculus. So if we didn't know this, we probably wouldn't know the fundamental theorem of calculus. So that's why it's also kind of important. It's one of those. It's one of the pivotal theorems. This theorem gets us a lot of, gives us a lot of bang for our buck. But first, we're going to talk about mean value theorem's little brother. It's called Rolle's theorem. It's kind of the mean value theorem in a very special case. Let me tell you what Rolle's theorem says. Let f be defined on an interval AB and assume the following conditions hold. 1, f is continuous on AB. 2, f is differentiable on the interior of AB, on the open interval. So f is continuous on the entire interval, the closed interval. It is differentiable at all points inside the interval. And 3, f of A is equal to f of B. So the endpoints give you the same value. Okay. Those are all the assumptions. Pretend you have a function that fulfills those 3 assumptions on some closed interval AB. Then there's a conclusion that you can make. Then, here's what you'll be able to say. There is some C in the open interval AB. There exists some number in that open interval such that f prime of C will give us 0. This is called Rolle's theorem. Consider a function on a closed interval. If it's continuous on the closed interval, differentiable on the open interval, and the endpoints give us the same output, there has to be a point inside the interval such that the function will give me, the derivative will give me a value of 0. Here's some illustrations. Here's A, here's B. Suppose I have a constant function, f of x equals c, versus, here's A, here's B. F of B and f of A, these are all the same. So this is f of A equals f of B. But the function does something like this. Versus, here's A, here's B. Function does something like that. And again, I'm assuming that the f of A equals the f of B. So these are both on the same level. F of A equals f of B. Let's actually do some non-examples. Suppose my f of A is not equal to the f of B, but I'm continuous and differentiable. That's an example of such a function. Suppose my f of A equals f of B, but I'm not continuous on the interval. So something like maybe a hole, or maybe even an asymptote could work. So there's a point where I'm discontinuous. Rolle's theorem would say, tells us nothing about these two situations because the conditions aren't fulfilled. So here, does not apply. Here does not apply. But it applies to all the others. Now you'll notice here, f prime of c is never 0, this interval. It's always going to be a positive slope, it's a straight line. Here, you'll notice that f prime of c also never 0, that interval. The only place where f prime would have been 0 was at the peak, but the peak isn't existing. So we don't have this conclusion. On these, though, here I have a function that is continuous on the closed interval, differentiable on the open interval. In fact, f prime of c equals 0 for all c, right? So there's literally any point I pick in this interval will have this conclusion satisfied. If I look in this situation, well, there's a point here where the slope is 0. Notice that that point is in between a and b, just as the theorem says it should be. Here, there are actually several points where I have that thing happening. There are 4 possible c's that I could pick that will satisfy this, so the theorem is good. Here's also a non-example. A particular kind of illustration. A, B, different values. I want you to notice that there are points here where the derivative will give me 0. What I want you to notice here, we do have f prime of c equals 0 in AB, but I just want you to appreciate Rolle's theorem doesn't tell us that. We had to figure that out otherwise. So this is basically Rolle's theorem. In the event that you're continuous and differentiable and your outputs and inputs are at the same level at the endpoints, you're guaranteed there has to be a point in the interior where the derivative is 0. If you don't have that, then you might either not have a point where the derivative is 0, or you could have a point, but Rolle's theorem wouldn't allow you to see it. It's a blind spot in Rolle's theorem. So if the conditions aren't fulfilled, you have to check specifically yourself, all points. You have to just go through the work and do it. But in certain cases, you can know it's going to be there without having to actually work for it. Why would that be true? So the proof of this theorem. Suppose we have f on AB that satisfies conditions 1, 2, 3. Okay, so pretend we're in that situation. How do I know I must have a point where the derivative is 0? Then notice here, the extreme value theorem is going to help us out here. The extreme value theorem tells us, because of 1, f is continuous on a closed interval, absolute extrema must exist. There has to be an absolute max or min for this function. Now, there are 2 cases. One, the absolute extrema occur at the endpoints, or 2, the absolute extrema occur in the interior of the endpoints. I know they exist. Where are they going to be? Well, they're either going to be an endpoint or they're going to be not at an endpoint. Seems to make sense. Let's look at case 1. Let's actually write these in a different Roman numerals, I and double I. Let's look at case I. Case I will actually mean, this means f is constant. Why would f have to be constant in case 1? Well, that's the only kind of function where the max and min will occur at the endpoints and still be continuous and differentiable. If your max and min happens here, and your max and min happens here, what that means is you will never be higher than the endpoints. You will also never be lower than the endpoints, which means you always have to be at the endpoints. If you're continuous, the only way to guarantee that happens is if you're a constant function. And in this case, it would apply f prime of c equals 0 for all c. So I have found a point that the derivative is 0. It's going to happen at every point in this case. What if it doesn't happen at an endpoint? So I get the derivative is 0 if it occurs at an endpoint. Case double I. If the absolute extrema occur in the open interval, then, so the situation I'm in is, okay, here's your A, here's your B. Let's say the absolute max, for example, occurs somewhere in the middle. How do I know that the derivative has to be 0 at some point? Yeah?
Does the function has to change direction for that?
Sure, but a function can do that like a sharp corner. Derivative would never be 0 in that situation. How do I know a situation like this doesn't happen? We have the assumption that it's differentiable. So a situation like this is not going to happen because that would mean it's not differentiable everywhere. Right, so this situation is not the situation we're in this situation, a very nice situation. And in fact, Fermat's theorem tells us how to deal with a nice situation. Fermat's theorem tells us if the derivative exists, which is condition 2, it definitely does exist, and you are max or min there, the derivative must be 0. So then I get 0. F of prime is going to be 0. So in all cases, whether the absolute extrema occur at the endpoints or in the middle, I will be able to find points where the derivative is 0. In the first case, that's just because you have to be a constant function. In the second case, Fermat's theorem guarantees it. And we prove Fermat's theorem already, so don't have to do it. But we know we're in this situation in the first place because condition 1 allows us to use the extreme value theorem. Condition 2 allows us to use Fermat's theorem. Condition 3 is what guarantees that in case 1, I'll have to be a constant function. So with these 3 conditions in place, this situation has to occur. QE. Now you don't have to know the proof for Rolle's theorem, but you do have to know the statement. Unless you're a math and physics major, then you should try to understand the proof of Rolle's theorem. You won't need it for the test though, but consider it important to kind of learn. If you're an engineer or anyone else, you can just ignore everything I just said for the past 15 minutes. Just make sure you know the statement. So that's Rolle's theorem. I will give you an example after we talk about the mean value. So now with Rolle's theorem, I can talk about the mean value theorem. The MV, MVT. Here's what this theorem says. We have a function defined on a closed interval such that 1, f is continuous. On the closed interval. 2, f is differentiable. On the open interval. That's it. Those are all the assumptions we're making. So I'm not making any assumptions about the endpoints. I have a function that's continuous on the closed interval, it's differentiable on the open interval. There is a conclusion that I can make about this function. There is some c in the open interval such that f prime of c is going to be equal to the mean rate of change, the average rate of change. F of b minus f of a over b minus a. Mean value theorem is basically saying there's some point where the slope is the mean slope. Mean slope. Mean is just means average. Right? Remember, math people aren't very good at naming things. The mean is a kind of average. So you're basically saying there's a point where the instantaneous rate of slope change of instantaneous rate of change is the average rate of change. So the slope will occur, the mean will output the average value at some point. It's the average value theorem, or the mean value theorem. So this equation has to hold. And basically what that kind of means is, if I must, just to illustrate a situation here. Remember those situations where the Rolle's theorem didn't really apply? We can look at situations like that. If my f and my f of b and f of a aren't the same thing, my function is doing whatever it wants to do, and I measure the average rate of change, which means it's the slope of the line that goes to here, then the mean value theorem says I am guaranteed to be able to find some location where the tangent line to that is parallel to this line. That will occur at some point between A and B. Has to happen. Now, if I don't have continuity, there could be a gap here and it doesn't happen. And if I don't have differentiability, there could be a sharp corner there and it doesn't happen. But if we're continuous and differentiable, that's definitely going to happen. find the average rate of change, there will be somewhere in the interior such that the slope of the tangent line will be equal to the slope of the average rate of change. There's another way to think of this theorem. Basically, it says that okay, if you travel 80 miles in 1 hour, then at some point during your trip, you had to be traveling at 80 miles an hour. Right? So you drove somewhere, you got there in an hour, it's 80 miles away. Someone asks you, were you speeding? No, I wasn't speeding. They'll know you're lying, right? Because if you were always below 80 miles an hour, you would have taken longer than an hour to get there. If you're always above 80 miles an hour, you take shorter than an hour to get there. The fact that you got there in an hour means you had to cross 80 miles an hour at some point, which means you're speeding, right? So if you look at the average rate of change over the entire trip, there's going to be a point in the middle of that trip where your speed is exactly the average speed. This is called the mean value theorem, the noting that idea. And it's a very important idea, actually. Let's prove it. Here's what I'm going to do. I actually know what the slope of this thing is. The slope here is going to be f of b minus f of a over b minus a. The line crossing through that, therefore, I can think of a line passing through, say, this point, and I'm going to use that to kind of get a function. I'm going to compare f, proof of the MPT. Consider this function. I'm going to create a new function. I'm going to call a function g of x. What that's going to do is it's going to look at the function f of x, and it will compare it, or find the difference between that and a line that passes through x equals a with slope f of b minus f of a over b minus a. So I'm going to look at that function. Very strange function to consider, but don't worry too much about where that function comes from. Here's what's going to happen to it. It's going to be cool. Now, since f is differentiable, this means g is differentiable. Right? Because g is just f plus that. This is differential by assumption. That's just a straight line, so that's differential. So I can find g prime. The derivative of that, well, it's just a constant times x plus a constant. So the derivative is just going to be the constant. That's going to be the derivative. Now, ultimately I want to show that this has to be equal to 0 at some point, right? Because if it's equal to 0, I can take this and move it to the other side, and then I have f prime equals this. So that's what I want to show. This function will hit 0 at some point. How do I know it will hit 0 at some point? Here's something that's nice about this function. Right? So that's what we want to show. Look at this. No. at g of a, what would I actually get? Well, I'm going to go over here, plug in x equals a. This is going to be f of a minus f of b minus f of a over b minus a times a minus a. That's going to be 0, so I get g of a is actually equal to f of a. Okay? Note this g of b. That means I'm going to go here, I'm going to plug in b for x. I'm going to get f of b minus f of b minus f of a over b minus a times plug in b for x, b minus a. This is going to cancel with that. Then I'm going to have f of b minus f of b, that's going to cancel with that. Minus the minus f of a is going to give me f of a. So this means g of b is equal to f of a. But g of a is equal to f of a. This means g of a is equal to g of b. Now we can use Rolle's theorem. There is some c in AB such that g prime of c is going to give me 0. This means there is some point x equals c when I plug that in. G prime of c is going to be equal to f prime of c minus f of b minus f of a over b minus a, and that has to be equal to 0, which means I can now add this to the other side. For this point, my derivative is going to be that. QED. The derivative has to be the average rate of change at some point. Like I said, math or physics major, go home, read this over, try to follow what happened. Everyone else just know what the mean value theorem says, specifically. Here are some examples that we'll do next time. Try them for yourself. And we'll talk about them on Monday. Find all C in find all C that satisfy Rolle's theorem for this function. F of x equals x cubed minus 3x squared plus 2x plus 2 on the interval 0, 1, 2. Find all C that satisfy the mean value theorem for f of x equals x cubed minus 2x squared minus 4x plus 8 on the interval minus 1 to 1. Show MVP is false for f of x equals x to the 2/3 on minus 8 to 27. Why is it false? We'll do those next time, but be sure to try it yourself over the weekend. And we'll end there.